The next section of the course is going to concern a nucleophilic addition to the carbonyl. And this involves a new functional group, the carbonyl, which contains a CO double bond. But we often further classify carbonyls based on what else is attached to the carbon atom. In this particular section of the course, we're just going to be dealing with primarily aldehydes and ketones, which contain no other heteroatoms attached to the carbonyl. So a couple of examples here are things like formaldehyde, which is a dialdehyde. It's the simplest aldehyde. We, of course, have acetone. We have also acetaldehyde, which is kind of one of the simplest aldehydes. We have benzaldehyde. And we have acetophenone. And what all of these molecules have in common is that they have carbonyl groups. They have a C double bond O. And so we can think about these in terms of their frontier molecular orbitals. So the frontier molecular orbitals we're concerned about are, of course, the pi CO and the pi star CO. Okay, the pi bond is going to be the HOMO in this case, and it's polarized towards the oxygen atom because it's more electronegative. The pi star CO, of course, is the LUMO, and it's going to be polarized more towards carbon, which means that it has the more delta plus charge on the carbon atom. So let's take a look at what this would look like. And so say we have the barrel of a carbon-oxygen bond like such. We have one aryl group pointing out towards you and one R group pointing back away from you, which also means that we have two lone pairs pointing back away from you and two lone pairs pointing towards you. As I mentioned, right, we have a pi CO that's polarized more towards oxygen because oxygen is more electronegative. Okay, there is a nodal plane that lies in the plane of the carbonyl. The phasing above and below this plane have opposite signs, and that's a result of these orbitals originating from the two atomic p orbitals from carbon and oxygen, respectively. And we can also see that the dipolar resonance form for this molecule indicates that we've got negative charge on oxygen. So if we were to draw the resonance form which places negative charge on oxygen, we've got positive charge on carbon, you can see that the electron density is highly favored towards oxygen. So we have a dipole for this molecule. Okay. Now the LUMO is also important. The LUMO is the pi star orbital, and it's strongly electrophilic at carbon. And so if we were to draw the LUMO much the same way, we would draw it like this. But the LUMO is going to be polarized more towards carbon. Right? So it's strongly electrophilic at carbon due to the more delta positive that it has. And this is, of course, again due to that dipolar resonance form, which has positive charge on the carbon atom. All right, so most carbonyls react via their LUMO, not their HOMO, and thus carbonyls are really good electrophiles. And so there's a nodal plane in between the carbon and the oxygen, and so what happens is that the LUMO is going to look like such. And so the nodal plane between the carbon and the oxygen gives rise to this pi star orbital in which the biggest lobes are on the carbon atom. And this angle here, and there's sort of this angle here is 130 103 to 107 degrees. With respect to the plane of the carbonyl. So the lobes are kind of pointing out towards the R groups rather than symmetric with the nodal plane. And this is known as the Borohydride trajectory, or the Borohydride angle. All right, so this is the Borohydride angle. As I said, that the nucleophiles are going to come in and attack this pi star CO because carbonyls are very good electrophiles. What happens is when it populates that pi star orbital and breaks the pi bond, it's going to attack via that Borohydride trajectory. And so let's see what that would look like. So if we have just a regular carbonyl, right, some carbonyl here where R and R prime could be hydrogens or carbons. We have some nucleophile is going to populate the pi star CO. And once you draw the orbital is basically attacking that carbon atom as such, the electrons are going to move up onto oxygen as a lone pair. And so the net result of that is that you now have a new bond from the nucleophile to the carbon atom. And so that central carbon atom is going to rehybridize as sp3. Okay, and so we call this the tetrahedral intermediate. And this tetrahedral intermediate can go on and to do other things. So we'll just say stay tuned. Okay. All right, so this new sigma bond is formed between the nucleophile and the carbon, and the electrons move up onto oxygen as a lone pair, and this tetrahedral intermediate will then go on to do other things. All right, so let's take and look a little bit more closely at what would happen if the electrophiles, the aldehydes or ketones, were to react with a specific type of nucleophile known as a hydride equivalent. Okay, so this section is going to be called the irreversible nucleophilic addition. Okay, so let's take a look at the reduction of ketones and aldehydes. Reduction of ketones and aldehydes would give us a primary or secondary alcohols. Right? And this can be performed with what's known as a hydride equivalent. So hydride equivalent is a source of H-, but reagents like sodium hydride or potassium hydride are not suitable to reduce ketones and aldehydes. They're not very nucleophilic. They're very basic, but this is a result of the H- being very hard, small point charge. And so it prefers to act as a base and deprotonate something rather than act like a nucleophile. So the sodium hydride bond is too ionic in character. So what we use instead is a hydride equivalent, something that has H- like character. And there are really two molecules that fit this description. The first is NaBH4, otherwise known as sodium borohydride. And the other is LAH, which is sometimes abbreviated LiAlH4. And this is known as lithium aluminum hydride. And these two reagents are very similar, right? So the structure of sodium borohydride is going to be ionic with respect to the sodium, and the BH4 is also ionic, but there's high degree of covalency in between the borons and the hydrogen. So we have a sigma BH bond right, which is covalent, and that's going to be our nucleophile. In the case of lithium aluminum hydride, lithium is going to be positively charged. Our aluminum is going to be negatively charged, and again we have 4 hydrogens spanning the aluminum. And of course, this means that the sigma aluminum hydride bond is covalent, and it's going to be the thing that is nucleophilic. Right, so we have sigma boron hydrogen and sigma aluminum hydrogen bonds that are highly covalent and react by donating that hydrogen atom as the hydride equivalent, as that source of H minus. Right? So these react as nucleophiles and deliver the hydride to the ketone or aldehyde according to that mechanism that we had above. Okay, so generating that tetrahedral intermediate. So let's draw these mechanisms and see if we can see how these bonds are forming. The discussion of the differences between sodium borohydride and lithium aluminum hydride. We say that sodium borohydride is less reactive but more selective. And we say that the LAH, the lithium aluminum hydride, is more reactive but less selective. So what do we mean by this? Well, let's think about what would happen if we had 2 different types of functional groups. So the first one would be the sodium borohydride reduction. Right, in a sodium borohydride reduction, right, we say, let's say we have a ketone as our starting material. We're going to react with sodium borohydride and usually do this reaction in methanol as the solvent. Right, if we were to add an H minus across that CO double bond, we would generate a secondary alcohol as our product. So our secondary alcohol would look like this. Where the hydrogen is sitting on that central carbon atom, but we don't draw it in. So how would this look like in terms of mechanism? Well, we've got a coordination of the ketone to the sodium cation. We, of course, have that pi star CO as our LUMO. Right, we're going to have a boron come in. It's negatively charged. And what's going to happen is it's going to react one of those boron hydrogen bonds towards the pi star CO. It's going to then break the pi bond, and it's going to make a bond back to boron. All right, so this is a transition state, and notice I'm not using equilibrium arrows here, I'm just using a regular forward arrow, and we'll get to why this is the case in a second. But the net result of that set of arrows is that we now have a new carbon-hydrogen bond right here. We've got an oxygen bound to a boron with 3 hydrogens negatively charged, and of course a sodium plus counterion. Then we can undergo an equilibrium like protonation, and so what happens here is methanol as the solvent will come along and it will allow us to protonate that oxygen boron bond, and so the net result is that you get the alcohol as the product plus this species in which you've got the methanol attached to the boron. Okay, so this is the mechanism of the sodium borohydride reduction of a ketone. Of course, you can do the same exact thing with an aldehyde. So let's try to do an aldehyde, but this time let's use lithium aluminum hydride, and you'll see the similarities between these. Second to, right? And so this is an LAH reduction. We're going to use this time lithium aluminum hydride and a ketone, an aldehyde. All right, so the way we do this reaction is we normally do LAH in THF at minus 78 degrees. Right? It's a fairly powerful reagent. We'll get to that in a second. We follow this up by quenching the reaction with 15% sodium hydroxide. All right, this is aqueous sodium hydroxide. And of course, the product of the reduction of aldehydes with either LAH or sodium borohydride is an alcohol, or in this case, a primary alcohol. Okay, so we're starting with an aldehyde, and we're going to generate a primary alcohol. All right, so how does this work? Well, again, we're going to take our aldehyde, and we're going to coordinate that aldehyde to, in this case, lithium counterion. We've got the pi star, all right, CO as our electrophile. It's our LUMO. And our aluminum hydride here is going to deliver a hydride equivalent to the pi star CO. So there's our HOMO. So the sigma aluminum hydride bond is the HOMO. All right, we're going to get a tetrahedral intermediate, and this is an irreversible reaction, so it's a forward arrow, no backwards arrow. We've got now two hydrogens attached to that carbon atom. One was originally there, and the second is going to be delivered by the aluminum. We've got now an oxygen-aluminum bond, and then our lithium counterion. In the next step, we get exchange, so 15% sodium hydroxide in water will allow us to protonate the alkoxide, and that's going to generate your primary alcohol product plus aluminum hydroxide as a byproduct, which eventually kind of dehydrates to give you alumina. Okay, and so this is the mechanism for a lithium aluminum hydride reduction, and it proceeds via that same generic mechanism where you have the nucleophile attacks the pi star CO to give you a new sigma bond, and that new sigma bond forms this tetrahedral intermediate. The carbon rehybridizes to be sp3, and then that goes and does other things. In this case, it protonates to give you alcohols. Now, one thing we didn't mention yet is the difference between sodium borohydride and lithium aluminum hydride in terms of their reactivity. So let's draw out the following reaction. So let's say we have this benzene derivative, which has a carboxylic acid and an aldehyde. And let's say we react this with excess sodium borohydride in methanol. Right, so in theory, right, the sodium borohydride could react with both carbonyls, the aldehyde and the carboxylic acid. Now, you might not know exactly yet how to draw the mechanism for the carboxylic acid reduction, but in theory it could happen. Well, we said that sodium borohydride is less reactive. In this case, it's not going to touch the carboxylic acid. The only thing that it's going to reduce is the aldehyde. So the product of this reaction is going to be the primary alcohol with the carboxylic acid left untouched. By the same token, we said that lithium aluminum hydride is more reactive and less selective. So if we react this with excess LAH, so enough that it could react with both the aldehyde and the carboxylic acid, what we'll find is that it indeed does react with both. And so it's going to reduce the aldehyde to the primary alcohol, but then it's also going to reduce that carboxylic acid all the way down to the alcohol as well. And so the difference in reactivities between the sodium borohydride and the lithium aluminum hydride is a property known as chemoselectivity. All right, so chemoselectivity is when you have both two different reagents that can react differently with the same kind of functional group. And so in this case, we say that the sodium borohydride is more chemoselective. It will only reduce the aldehyde and not the carboxylic acid. And we'll talk a little bit more about the mechanism for the reduction of carboxylic acids a little bit later.